Hey everybody, here is the next video in our direction of EAS reactions. As a quick reminder, what we're looking at is this. What happens when there is already some kind of group on the ring and we want to do another EAS reaction? Well, so far in this zone, we have talked about activation and deactivation, which is entirely about electron density in the ring. We are also, and that's kind of the point of today, we're talking about directors. Some things are ortho-para-directors and some things are meta. Now there are two philosophies on how these work. One of them is electrostatic attraction, which was the last video we did, ATTRACTION, which is the last video that we did, and today we're going to talk about cation stability. So, quick reminder about point number one there. We never actually did the nucleophilic attack on the electrophile for that reaction. So that was simply based on where would the electrophile be more likely to be attracted on the aromatic ring. So for cation stability, ladies and gentlemen, this is going to be a lot of resonance forms. So first of all, let's put this as our aromatic ring, and the D stands for electron donor. And as a quick reminder, electron donors tend to be ortho-para directors. So let's go ahead and do that. So E plus. Now we're going to do the nucleophilic attack, and this is all about the resonance forms. So there's our first resonance form. Move the pi bond, draw the second. Yes, you probably should be writing all of these out too. It will help you, believe it or not, in your understanding of this. And then finally, the last one, or is it? That cation, which has another resonance form. In fact, that's so important, I'm going to draw it in a different color. Another resonance form that looks like this. And rule of stability, more resonance forms means more stable, means favored. Now, what I want you to do is I want you to do the same analysis, but with our D group there. If the electrophilic attack occurs off of the meta carbon, so this is ortho, this one is meta, and then the third one I want you to do is the para attack. Now, go ahead and do all these. It's good practice for you, which I know most of you hear and interpret as, I'm not going to do it. It's good practice for you. And we'll be back in just a minute to talk about the resonance forms. All right? Surprise! There are the answers. All right. So what we see is for an electron donor, if you add to the ortho or the para position, you get this extra resonance form, which means the cation is more stable and that is a more favored overall structure. What about if you add meta? Well, the meta isn't bad. You just don't have the extra cationic structure going on. Now, what I'm hoping you're starting to see again is this every other atom pattern. It's very important. Okay, now, what if we have on our aromatic ring a withdrawing group? All right, now we have an electron withdrawing group with a positive charge there. We're not going to talk about it actually pulling electron density out of the ring. What we are going to talk about here, though, is what happens when, with the electron drawing group there, you do an ortho attack, a meta attack, and a para attack. Sorry, that was a text. All right. So now, what I want you to do is the same thing we did before. Draw all three of these in a resonance form, and then draw all the resonance forms and show me any extra that are advantageous, if any. All right, so go ahead. I'll let you work on this, and I'll be right back. So before I show you the answers, I just wanted to show you this really pretty picture of a fire opal that I found. Doesn't it look like it's a really yellowy sunset and all those discolorations in there look like light coming through clouds? I thought it was pretty. So here are the resonance forms for when you do an electrophilic addition to a ring that already has an electron withdrawing group on it. And what you see in the two in red that I drew in there are particularly unstable. Why? Well, moving past the fire opal, what ends up happening is, remember, cations are voids of electrons, and they try to pull electron density around from everything in its environment. You've got two cations here that are fighting over any electron density that's left. That is really destabilizing and a really not favored state for this molecule to be in. Pretty fire opal. But then, so we go to, if we add into the ortho or the para position with an electron withdrawing group, then the problem we run into is we generate these two really nasty, high energy resonance forms. But if we add meta, we manage to skip all around having those two cations be on adjacent atoms. So just like we saw before, it's not like meta is particularly good. It's that meta sucks less. All right? Meta just flat out sucks less. All right, so one last thing I want to show you, and it is this. We keep coming back to this. I know we've made a couple additions, but this is still really important. Knowing what's on your ring and knowing subsequent reactions are pretty critical. Now, this is the last video for today. Tomorrow, which would be Wednesday, I'm going to put up one, maybe two, about how you do some synthesis based on what you already have on the ring and the order in which you need to add things. All right? Then that will be the end of new material for Organic 2. We'll be done by tomorrow, and then you'll have everything in your hands. Check your email. I changed the due date for the toolkit. I gave you the list of reactions for the toolkit, and everything should be good. All right? See y'all later.